Okay, hello everyone, welcome to my presentation. So my name is Cheng-Sheng Huang. Currently I'm working with the Department of Mechanical Engineering at National Chaudhery University. So today I'm going to talk about the work I was working on with the Professor Brian Cunningham while I was at the University of Illinois during my postdoc. So the topic of my today's talk is the quartz-based photonic crystal surface for multiplexed cancer biomarker detections. So here's the outline of my today's talk. First, I will briefly introduce the background and motivation. Then I'll talk about the photonic crystal in general, how we use the photonic crystal for level 3 measurement and for the enhanced fluorescence measurement. Then I'll briefly talk about how we fabricate this quartz photonic crystal. Then I'll talk about how we can use the sandwich assay to detect cancer biomarkers. And for that, I will bring some preliminary results and some discussions. And I'll finish my talk with a brief summary. So our ultimate goal is to develop a sensitive antibody microarray for breast cancer screening. So the breast cancer is a very serious problem, especially in the modern society. It's the second most common cancer among American women, and it's the second leading cause of cancer death in women. So the chance of developing this invasive breast cancer in women's life is about 12%. So today the mammogram is the recommended tool for breast cancer screening and diagnostics. However, its sensitivity is only about 68 to 88% based on different studies, and it's less than 50% for younger women, and it's only about 25% for patients with hormone therapy. Also, the mammogram is subjected to a doctor's interpretation. It also requires the tumor size to be 0.5 centimeter in diameter or larger to be able to detect it. So there is a need for a better screening and diagnostic tools, and that's why we want to develop this antibody microarray to better screen and diagnose breast cancer. So today the most commonly used substrate for the microarray application is the regular glass. It's a regular glass, and the detection often involves the fluorescent dye molecule, which are captured by their complementary binding partner. So the specific analytes can be identified, can be quantified. However, in order to detect these low abundance cancer biomarkers, the amplification of the fluorescent signal is often needed. Based on that mechanism, they can be categorized into chemical-based or substrate-based. For the chemical-based, they are thermine signal amplification system or the rolling circle DNA amplification. So these two are the most commonly used chemical-based method to amplify the fluorescence. So instead of using this regular glass with this chemical-based technique, people try to develop different substrate to amplify this fluorescence directly, such as the metal enhanced fluorescence or different micro-nano texture surface. So our lab are working on the photonic crystal to enhance the fluorescence, which is the work I'm going to talk about today. So next I will briefly talk about the mechanism of the photonic crystal and how we fabricate this. So the photonic crystal used in this work is also known as the guided mode resonance. So basically it consists of wave guiding layer and also the grating structure. So when the incident light, at the right combination of this incident light wavelengths and also the incident angle, the light will be coupled into this wave guiding layer to excite the resonance. So when this happens, there are two unique properties that's used in this work. So the first property can be realized at the far field response when it's on resonance. So here shows how it works. By inputting a broadband light source, a specific narrow band of light will be reflected back when it's at resonance, and the rest of the light will be transmitted through, as you can see from this reflection spectrum. So here is for the reflection for TM and TE polarization. So this wavelength is highly dependent on the refractive index on top of the sensor surface. So once the index is changed, this wavelength will be shifted accordingly. So by monitoring this amount of shift, we can actually correlate how much the biomolecule is deposited on the sensor surface. So the second property is the enhanced near-field electrical field intensity. So here you are looking at the one period of photonic crystal structure. So here shows the cross-section. So when it's on resonance, the electrical field can be built up inside the waveguide layer and also on the surface of the structure. So as you can see here, shows the simulation for the TM polarization and TE polarization. So electrical field intensity can be enhanced by up to 100 times on the sensor surface for the TM polarization. And because the emission of the fluorescence is proportional to the excitation electrical field intensity, so when we excite the resonance on the photonic crystal, we can actually have enhanced excitation on the fluorescence molecule, that's why we can have the enhanced fluorescence. So to fabricate this quartz photonic crystal, we use this step and flash imprint lithography. So here shows the detailed fabrication steps. I won't go into detail. The basic idea is that using a template with the grating structure, and we can transfer this into this imprint resist. And after the curing with the UV light, we can release this template, and followed by a series of the reactive ion etching to transfer the pattern into this substrate. And lastly, we can coat the TiO2 to make the photonic crystal. So here shows the actual photonic crystal used in this work. So we cut this into a 1 by 3 inch, which is the size of the regular glass slice. And on this slide, there are 2 by 8 grating patterns. Here shows the cross-section of the SEM image. So the grating depth here is about 40 nanometer. The period is 400 nanometer, and the thickness of this TiO2 is about 140 nanometer. So here shows the transmission spectrum. So one resonance, when we illuminate the light at the normal incidence, there's one resonance around 690 nanometer. And when we illuminate this light at 11-degree incident angle, there's another resonance at 633 nanometer. So we will use these two resonances for label-free and enhanced fluorescence. So in order to demonstrate this photonic crystal for the microarray applications, so here we select 21 different cancer biomarkers from different protein families to demonstrate this. All these cancer biomarkers has been associated with the breast cancer. So to do the measurement, to do the detection, we use this so-called sandwich assay format due to its high sensitivity compared to direct labeling technique. So here shows how we do this sandwich assay. We start with the photonic crystal substrate. Then we print this different capture antibody using non-contact printer. And after that, we apply the blocking solution to block the rest of area to prevent any further non-specific binding. Then we apply the sample, followed by the biotin-related detection antibody. And the last step is to incubate with this strep evidence Sci-Fi, which will give us the fluorescent signal. So here shows the actual array layout. So as I mentioned in the beginning, we separate this into 2 by 8 wells. In each well, it consists of 4 identical replicates. So what you are seeing here is the antibody we printed on the slides. So in each replicate, it consists of the 30 spots, which includes the 21 different antibodies and some positive and negative controls. So after the antibody is printed, we can apply different samples at each well to measure the concentration of the analytes. So next, I'll bring you some preliminary results from the label-free measurement and also from the enhanced fluorescent measurement. So in order to detect both fluorescence and label-free, we build the microscope in our lab. So here shows the schematic of the microscope. It consists of two lasers, helium-neon laser and also aluminum gallium arsenide semiconductor laser. And this tunable mirror allows us to adjust the incident angle to pass through this photonic crystal. And the transmission will be collected by this objective lens, which is coupled to this CCD to measure the intensity. So just to remind you, we designed this to have two resonance. So at normal incidence, this 690 nanometer laser will have resonance actually around 0 degree, which we'll use for the label-free measurement. And for the helium neon laser, we will illuminate at around 11 degree to excite the resonance for the enhanced fluorescence. So here shows the label-free measurement. So the basic idea behind this is that before we deposit this antibody, the resonant angle of the photonic crystal is around 0.8 degree. So after that, we print this antibody. The more antibody we print on the surface, the more resonant angle shift it will cause. So the data here shows after we print this antibody, the resonant angle will shift from 0.1 degree from this EGF and HGF up to 1 degree from this UPAR. So this data imply two things. So first, even we print all this antibody at the same concentration, they actually cause different resonant angle shift because different antibody will have different capability to bind with the PC surface, which cause the resonant angle to change. So what this means, for the following enhanced fluorescent imaging, we cannot use a single fixed angle to scan the whole slice because their resonant angle will be different. So to overcome this, we developed this angle scanning technique. So instead of using a single fixed angle to scan this photonic crystal slice, a range of angle is used to scan the whole photonic crystal slide. And the maximum intensity from each pixel will correspond to the illumination angle that's closest to the actual resonant angle. And the maximum intensity from each pixel will be selected to construct this final image. So from these two images, it's very clear that using this angle scanning, we can have a maximum fluorescent enhancement. And also we can have more uniform enhanced fluorescence. So the data here shows by using this angle scanning technique, we can actually improve this CV by up to 99%. So here shows three examples for the dose response curve from three different assays. So again, here tells us two things. Using this angle scanning technique, which is the black curve, we can have higher fluorescent enhancement, and also we can have more uniform fluorescent enhancement as indicated by this smaller deviation. So using this angle scanning technique, we can detect the all these markers between 6.3 to 500 picogram per mil for different assays. So here only the assay with the R-square value greater than 0.95 from the 4-parameter logistic model curve fitting are selected. So to quick summarize what I've talked about today. So I talked about how we utilize two distinct properties from this photonic crystal and how we fabricate this and how we can use this sandwich to detect these cancer biomarkers. Then I have demonstrated that we can do both label-free and enhanced fluorescence using the Quartz photonic crystal and the home and house-built microscope system. And this label-free measurement shows that different antibodies actually have different binding capability on the sensor surface, which causes the resonant angle will be different. That's why we developed this angle scanning technique to detect, to enhance, to have the maximum fluorescence enhancement. And lastly, using our technique, we can detect this cancer biomarker per 26.3 up to 500 picogram per mil. So I would like to acknowledge the funding from NSF and NIH. So if you have any question, I will be happy to discuss with you.